Okay, so it is recording. Students online, do you hear me well and see my screen, right? Yes? Perfect. So as I mentioned, I welcome everybody to the theoretical lecture. Professor Aki is still on trip, so I will substitute him today. Before starting the lecture, I wanted to mention the structure and also address some questions that I have received related to one of the assignments and the simulation project work, okay? So today, just to have so that you have the structure in your mind, we are going to finish with the modeling of hydraulic components. So we are going to learn how to model the hydraulic cylinder and the pump, okay? Next, I'm going to do an exam exercise, which is this solving this hydraulic circuit with the hydraulic equations and all the terms. Basically, you will find there all the components that we have been working with, okay? And after that, I want to start. If you remember, there was one theoretical lecture that basically you didn't have that day lecture because Aki had a flu. You remember? It was a Monday. So today I'm going to provide you the theory of that lecture as much as I can, okay, in terms of time. But I don't want to sacrifice anything in the hydraulics. So let's see how much I'm able today to provide of these slides. So in terms of material, today we are going to retake the lecture with the PPT week 10, okay? PPT week 10, and in particular in the cylinder, okay? In the cylinder slides, which is this one, okay? And one comment related to this, the slides of week 10 have been updated in Moodle, okay? So just in case you downloaded the ones of the last week, I have modified some small details in this last slide. So please download them again. And for the exam, review them, okay? This final leg. So before starting the lecture, some comments. I have many questions related to the simulation project work that I have not replied yet, okay? Because all the questions came together and I have like a big wave of questions. So I'm planning to reply all these emails together. But just in case you didn't receive a response, it is because I received all of them basically Thursday, Friday, and there are a lot of questions. So I will reply all of them. And also tomorrow we can solve some doubts, okay, in the tutorial about the simulation project work. And the other thing, I have received one question related to assignment 9 that was related to the computation of a natural frequency. Related to this question, just to give you a hint, okay, if you remember, I have it here in the slides called week 9, the ones that you have in the Moodle, there was one exercise where you had to compute, if you remember, the natural frequency assimilating this oil as a spring. So basically you had to take into account the flexibility of the spring and the stiffness of this oil, and using the bulk modulus, you obtain a relation that related basically this stiffness, assimilating the behavior of the oil as a spring with the hydraulic circuit parameters, okay? So this may serve you as a hint. This exercise may serve you as a hint for this assignment, okay? You can find this exercise if you want to redo it for practice for this assignment in slides 18 and 19 of week 9 slides, okay? Just to review for assignment 9. You have there a clue of the exercise. Yes? Yes.
Mass, or will it be the mass multiplied by the lever arm?
That is something that you need to think, okay, to figure out. So I give you the hint because in this natural frequency you have two main parameters, let's say the stiffness and the mass. The stiffness you directly compute it with this exercise. You can basically learn here how to derive the expression of the stiffness in terms of the hydraulic parameters, and for the mass try to figure it out, okay? But it's very simple, okay?
Would you provide some source that we could use to
try when is the deadline of that assignment?
Sunday.
Okay, so try to think about it during the week, and if it's Friday and you still have not figured out, we can talk about it, okay? But yeah, you will see that the exercise is very simple. The basically you have here the hint to compute the K, and if you think about the mass, it's easy, okay? Any other issue for the simulation project work? We talk about it tomorrow, okay? More in the tutorial, okay? Very important. For tomorrow, please also attend the tutorial. I'm going to finish all the hydraulic components modeling for your simulation project work. So from tomorrow, you basically can complete the simulation project work. Okay, I'm going to provide you the program for the hydraulic cylinder. It's basically the same as the one that you need to use in the simulation project. Okay, so please attend either in person or online, because you can ask many questions. And after that, I'm planning, if I have enough time, to solve another exercise example of hydraulics for reviewing for the exam, okay? So I'm going to provide between today and tomorrow as much as material as I can for review for the final exam, okay? So let's go for it. This was just a comment for the assignment 9. Let's ask for the students online. Do you have some question about the program of today and tomorrow? Is it clear? Yes? All good? Would you like to ask something or work in some of the other problems? Okay, so let's start. If you remember, last week we were talking about the modeling of the hydraulic components. Let's put this in projection mode. And I stopped in the cylinder, okay? Which is exactly also the point where I stopped in the tutorials. And in the cylinder, basically, we mentioned the function of this component, which is basically transforming the hydraulic pressure into a mechanical force. And we provided, if you remember, the expression, okay? The expression of this force is given by the area A1 times the pressure, where A1 and P1 are the areas and the pressures in the piston side chamber. Remember that if you have the piston moving inside the cylinder, this chamber here, we denote it, or we call it piston side, okay? Piston side. And this other side, where you have an area A2 and a pressure P2, is piston rod side, okay? Because you have the piston with the rod here. Sorry, I think that for the students online cannot see my mouse cursor. Perfect. Yeah, I remember. So you have here the piston rod side, and here the piston side, okay? A1, P1, and here piston rod side, okay? And the force provided by the cylinder is basically the difference between the product of the areas times the pressure, A1, P1 minus A2, P2. And we have to consider an additional term that is very important in hydraulics, which is, do you remember? The friction force, okay? Friction force that you can see in this expression as a sum of different forces. Do you know why it is a sum of different forces? The reason is that there are different sources or different points where you have friction in this hydraulic cylinder, okay? Basically, the friction comes between the seal material that you can find in the walls, for example, of the piston and the rod, with the wall themselves of the cylinder, okay? So if you imagine this piston, okay, the material of the piston has a friction with the cylinder wall, and in the same way, this rod here has a friction with the cylinder wall, okay? So you would have here two sources of friction, this F mu1, okay, which is between the piston and the wall, and this F mu2, which is the friction between the rod and the wall, okay? That is why you have here the sum of this F mu, okay? Because there are different sources. And you have here the explanation of this friction, the origin, okay? Because of the contact between the seal material in the piston and the rod with the cylinder walls. Effect of this friction force. It is a damping force that allows you to reduce the vibrations or oscillations in your hydraulic circuit. If you have already worked with your simulation project work and you have tried to model some of the hydraulics there, or even in tutorial 6, if you remember, we found some oscillations in the pressure. You remember? So you could try to mitigate, to reduce these oscillations, playing with the parameters of the friction force, for example. Okay? Perfect. And now, how to model this friction force? In hydraulics, this friction force is a very complicated phenomenon, and it is a function, is dependent of several things, okay? For example, the speed of the piston, the pressure difference between the chambers, the sense of motion, the sealing material that you use, different sources, okay? Here, we are going to learn how to model in a very simplified way this friction force, okay? And the expression that we are going to consider is this, okay? So basically, this friction force, F mu, is going to have a similar structure as the force itself, okay? So now we are going to focus on computing this term here, the F mu, okay? And if you see, the force itself is given by the difference of the products of areas times pressure, no? So we are going to assume that our friction force is the term that we had, so the products of the areas times the pressure, multiplied by an efficiency, okay? An efficiency, this eta symbol that you see here is the efficiency coefficient, okay? And multiplied by a function, this chi function is a function of the speed of the piston, okay? Speed of the piston. And you can obtain it, for example, from different measurements, okay? Different experimental measurements on cylinders. This is the structure that we are going to consider. So basically, three main components, okay? This function of the speed of the piston, which is obtained from measurements, the force itself without that we saw before, given by the difference of the areas and the pressures and the efficiency coefficient, okay? So basically that is what you need to know about the cylinder. Tomorrow, the program that we will do in the tutorial will be completing our custom template, if you remember, computing this equation, okay? This was the equation that I was not able to complete the other day. So we are going to finish it tomorrow. Perfect. Just this is general knowledge, okay, for you in terms of physics. You can see here a force balance in your cylinder, okay? So basically, this side would have here, this distributed force here is the pressure, okay, in the piston side. So the net force, the total force would be A1 times P1, which is this expression here, okay? Sorry, this expression here, A1 P1, okay? The net force here. On the other side, one question that I have for reviewing for the exam. The surface, the acting surface in this side, which geometric form does it have in the piston side? It is a circle, right? It is a circle. So we would have this A1 would be the surface or the area of a circle. Now, for practice for the exam, this other force, which is A2 times P2, A2, which form does it have? Which geometry does A2 have? Without any fear of answering bad, we are here to learn, okay, and to review. Annulus, okay, exactly. It is like a circular crown, okay, circular crown. So basically, we would have here a big radius R1 and a small radius R2. So this would be a circular crown, okay? Perfect. Perfect. Nice. So basically, what I wanted to mention here is that you have the equilibrium of forces in the piston side, piston rod side, and the friction forces, okay? Perfect. So let's move to the next component, which is the pump, okay? In this course, we are going to work with, have you ever worked with pumps before in some courses? Is the first time? Maybe you have heard about them, but you have not studied them in detail, no? Probably.
Just a little bit.
Okay, perfect. So basically, here we are not going to, let's say, put a lot of detail in the pumps because it is a very wide field, but at least we are going to explain the basics, okay? The idea here is that the pumps transforms the mechanical energy into hydraulic energy, and how does it operate, okay? So basically, maybe if I ask you, what does a pump do? You might reply, well, the pump provides pressurized fluid, no? Provides fluids that has a higher pressure into the hydraulic circuit. Well, that would be correct, but in more detail, the, let's say, real function of the pump is displacing the fluid by varying the chamber inside, okay? So basically, we are going to consider that the pump is not actually creating, let's say, pressure by magic, but what it is doing is providing volume flow, and this volume flow is constrained, is restricted inside, and because of this constraining, you create the pressure, okay? That is the mechanism that the pump employs to pressurize the fluid, okay? Constraining the fluid that is displacing inside, okay? You can read it here in more detail. The content that I'm providing is basically the one that you will study in the slides, okay? So with more detail. So here, the pump is not actually creating pressure, but volume flow, and this fluid pressure is formed when the volume flow is restricted, okay? How are we going to model the pump? Well, you already know the symbol from the exercises, okay? And basically, if we have the pump, there will be some equations describing the dynamics of the pump. As mentioned, the pump provides a volume flow, which is this QP, and this QP will access into a control volume that, based on the lumped fluid theory, you already know how to model using the classical equation that we mentioned the other day. Do you remember, with the effective bulk modulus, the volume, and all the incoming and outgoing flows, okay? So this is how we are going to consider, okay? Perfect. types of pumps that we are going to consider here. There are two main types that maybe you have heard about, okay? Fixed volume pumps and variable volume pumps, okay? Usually in industry, how does this pump work? We usually have a motor that is spinning, okay? And this motor drives a pump, okay? Drives the pump. And these motors are usually designed to work with a constant rotational speed, and the pump is driven, okay? Main equation that you need to know in the pump, in the fixed volume pump, well, in this case, is this one, okay? This is the output power, the power that is given by the product of the volumetric flow rate times the pressure, okay? So in these pumps, the output power is equal to the volumetric flow rate times the pressure. Restrictions that you might have in the volumetric flow rate of the pump, because if you remember, we mentioned that this pump provides a QP, you know? QP. Restrictions in this QP. First, the maximum fluid that the pump can address, that will be denoted by Qmax, okay? And this maximum volumetric flow rate is a function of the rotational speed and the pump displacement. And there could be another restriction that I will show you, okay? So basically, if you have the pump here, this would be the equation. This volumetric flow rate that comes from the pump can be either the maximum flow rate from the pump or the one given by this equation. And I'm going to explain it very easily, okay? Imagine that you have a motor driving a pump, and the motor itself has a maximum power, okay, that can provide. You agree with me that if this is the power, and we write here instead of power, Pmax, the maximum volumetric flow rate that the pump can provide is constrained by this maximum power, right? If we have here Pmax. So basically, this equation, this QP, comes from isolating Q in this equation. So we are going to consider a motor that can provide a maximum Pmax. And if you obtain Q from here, this Qmax is just, or QP is just the maximum power from the motor divided by the pressure of the pump, okay? The pump is designed to work at a certain pressure. So the maximum volumetric flow rate is given by this power divided by the pressure of the pump. What happens? That usually the pumps has a efficiency, a mechanical efficiency, okay? That is why you can find here in this equation an eta, a coefficient, that is basically the efficiency of the pump, okay? So do you understand this equation? Basically, the meaning is that the volumetric flow rate coming from the pump is either the maximum, is the minimum between the maximum volumetric flow rate that can address the pump, or if this one is more, let's say, limiting than the other one, the maximum power that can provide the motor, okay? So you can have either a constraint from the volumetric flow rate of the pump or a constraint from the motor, okay? Is understood that equation? Yes? Perfect. So QP will be the minimum between these two. Perfect. These were the fixed volume pump. Now we are going to learn a second type of pumps, which are called the variable. Well, let me check for the students online. Any question so far about the hydraulic cylinder modeling? Sorry. And there are some comments. Okay, perfect. Some questions about the pump modeling? Everything good? Okay. So far? Did you understand how to obtain the volumetric flow rate QP? Yes? Perfect. Okay, so let's continue. And now we are going to talk about the variable volume pump, okay? And in this particular case, in the variable volume pumps, the volumetric flow rate, QP, can be changed without changing the rotational speed of the motor, okay? In this case, there is a controller that allows you to vary the volume inside the pump, and this controller has a characteristic time constant between 0.1 to 1 second that allows you to vary the volume inside the pump, okay? So basically the idea would be fixed volume pumps, okay, and variable volume pumps. The symbol in this particular case changes, okay? In the fixed volume pumps, this is the symbol that we consider, and in the variable volume pumps, you will see, we also mentioned, I think, this in the tutorials, if you remember. These pumps have an arrow here representing the variable volume, okay? And there are two control strategies for these pumps, okay? One control strategy is constant pressure control, and the other one is load sensing control. I'm going to put you now a video explaining the most difficult one, but basically the idea is you have a pump that has a variable volume, and the idea is that with the constant pressure control, you are going to control the outlet pressure so that it is constant, okay? You are going to provide a pressure that is constant all the time. And with the load sensing control, you are going to detect with the pump which is the maximum peak of load, the maximum pressure in your circuit, and you are going to adapt the pressure drop so that you can overcome or guarantee the maximum load pressure in your circuit, okay? So basically this one always provides the same pressure, and the load sensing control allows you to detect the different pressures that you have in your circuit, and you vary the outlet pressure, okay? Controlling this drop pressure. I'm going to put you first the video, and now I'm going to explain the questions, okay? Please, it's very important that you understand this. Just in case we have something, I have already the videos without advertisement here, so let me show it to you.
Bite-sized and just for a drink. Hey, it's Carl here from lunchboxsessions.com. This will be a brief introduction.
This is the load, okay? The hydraulic cylinder.
Sometimes referred
And this is the pump.
as flow compensating. Our pump still has that very heavy spring, that major adjustment called the pressure compensator or the pressure cutoff for when we hit that really high top end pressure to make sure our system is protected. But it also has a weaker spring called the load sensing adjustment or the flow compensator. And that flow compensator is receiving information, feedback, if you will, coming directly from the load, our cylinder, which right now is working at 300 psi. That's the pressure it takes to lift the cylinder and rod. And that 300 psi is being fed back to the controller and giving that spring a boost. I could tell that the spring is actually set to 300 psi. How did I figure that out? I figured that out because our pump outlet pressure is set at 600. So it's taking 300 from the load and adding it to the 300 spring setting. And those two pressures add together, those two forces add together to give us our regulated pump outlet pressure of 600 psi. This is different from a pressure compensated pump, which might be set at, say, 2000 psi at all times, and therefore using a lot more input energy. So in this particular case, we've got a pump that sets its outlet pressure just slightly higher than what's needed by the load. We've got to have some kind of a flow controlling device in there. This is our needle valve that's being used to set our desired cylinder stroke speed. But let's have a look at what happens when I add a brick to the brick stacker. Our load pressure has gone up to 600. Well, what happened to our pump outlet pressure? Somehow it automatically adjusted from 600 up to 900. What we're finding out is that we're always maintaining a 300 psi pressure differential, sometimes referred to as a 300 psi margin pressure when we're referring to load sense systems. Let's add one more brick, and this time watch the delta P gauge. The delta P gauge fluctuates for a brief fraction of a second, but quickly we find it returns to 300 psi, and we never really noticed any change in speed at the cylinder. The cylinder just kept moving nice and steady, and our pump found out that it needed to increase the outlet pressure setting automatically. So what we found out is we can have a pump that is set at a pressure that's just a little higher than what's needed at the load, instead of being always at the pressure cutoff pressure, which could be considerably higher. And because we know we want steady speeds to our hydraulic cylinder, we don't wish to see any fluctuation in speed. Every time we take a brick off the stack, or every time we add a brick to the stack, the pump knows to adjust itself accordingly so that the flow rate through the needle valve doesn't change. That's the nature of a load sense system, and that's a brief introduction to load sense pumps. Thanks.
So to summarize, this was the functioning mechanism of the load sensing pump. And if you have noticed, basically, the idea here is to maintain in this valve a pressure drop or a pressure margin that is constant. So you can adjust here the load Depending on the number of bricks that they were adding here, the required pressure to lift the cylinder was increasing. So basically, depending on this load, the controller here receives the information and your pump works in a way so that this pressure drop is constant, okay? This is the principle of functioning of these load sensing pumps. In a constant pressure pump, what would be constant is here, the outlet pressure from the pump. But in the load sensing pump, the second control strategy, what is constant is this, the pressure drop with respect to the load. Is this clear? So in one, the constant is the pressure margin or the pressure difference. And in the first strategy, what is constant is this pressure. Is clear? Yes? Perfect. I had one comment saying that this kind sounds of a PID controller. Well, indeed, since you have a controller, you can basically implement different control strategies to provide the information to the pump. Okay, you will study this in more detail in a course that is provided after Christmas, that is control of mechatronic machines. So those of you who study this course, you will learn different control strategies, and one of them will be the PID controller, okay, to model this. So did you understand how do these variable volume pumps work? Yes? Perfect. And now with this, I can move to the equations, okay? To the equations here. So if you remember, in the fixed volume pumps, the equation was very easy. Basically, QP was not given by a differential equation. You don't see here a time derivative. You just say that the QP is either the minimum between the maximum volumetric flow rate, or if you have the motor restriction, this power restriction. But in the variable volume pumps, you have a differential equation for this QP, okay? It is not just that QP is equal to a number. It is that QP is modeled by this differential equation. And in the constant pressure control, basically, you have here this Pref is the reference pressure that you want to achieve, and PP is the outlet pressure in the pump, the pressure provided by the pump. And in the load sensing control, remember, you don't work with the outlet pressure, but instead of working with just these pressures themselves, Pref and PP, you work with delta pressure drop or pressure margins, okay? That is why in the load sensing control differential equation, you have these delta pressures, okay? The pressure drop in the valve that I showed you in the video, okay? Is it clear? The equations, the connection, perfect. This max in this equation, maximum between P1, P2, Pn, is because imagine that you have several cylinders in your hydraulic circuit. You need to provide a pressure that is enough for lifting the most restricted pressure, okay? That is why you have to distinguish between different pressures. In the previous example, you only had one cylinder, but you can have many of them and many loads, okay? That is why you have to distinguish between, or you have to choose the maximum between them, okay? But you can see that the structure is very similar of the equation. So that was everything what I wanted to tell you about variable volume pump. This was the video that I showed you. This is an example of a hydraulic circuit. I'm not going to put much detail, okay? But basically, this would be the variable volume pump. This would be a directional control valve. And you can have here the hydraulic cylinder. Instead of this figure, I highly recommend you to watch the video that I showed you, okay? Because basically, it works the same way and is much more illustrative, okay? And this is the same equation as I showed you before. This final slide that you see here is the static characteristic curve. Have you ever heard about the static characteristic curve of a component, of a mechanical component? Yes. Basically, the static characteristic curve is describes how your component works in a steady configuration. Okay. In a steady configuration, I mean that if you go to the equation, to the differential equation here, a steady configuration means that your time derivative is equal to 0, okay? So basically, if you make this derivative equal to 0, you can obtain a relation between the volumetric flow rate and the pressure, okay? And if you make this 0, you will obtain a linear relation between the volumetric flow rate and the pressure. That is what is depicted in this figure, okay? Basically, is this a straight line that you can see here, and this relation comes just, what you need to know here is just that you obtain this curve by doing the time derivative equal to 0, and that is called the static characteristic curve of the pump, okay? And basically you obtain a function between QP and the pressure by doing QP dot in the previous equation equal to 0, okay? So that was everything that I wanted to ask you. Now, to show you. Now, I think that I have activated the quiz. Can you check it, please? And let's do the first of the quizzes. Let me check. I have it here. For the students online, do you have some question? I think I replied. Yeah, I replied to the question of Johnny that, yeah, well, the comment exactly that it sounds like a PID controller. You will study more about that in the next course. So everything clear for the so far about the cylinder and the pumps? Yes. If you have any question, please feel free to ask. Okay. Perfect. So now let's go to the quiz. It's available, right? It is available, no?
Yeah, yeah.
Yes. Okay. So just in case that some of you don't have it, in a hydraulic model, a pump is a sum to produce, and the options are pressure for a hydraulic circuit, oil flow for a hydraulic circuit, temperature for a hydraulic circuit, and voltage to electric circuit. Remember what we mentioned. How are we going to model the pump? Okay. How are we going to model the pump? We are going to a sum that is going to provide something to the hydraulic circuit that is, and we even wrote the equations about how to compute that. I'm going to give you a couple 1 minute, and we will see now the answer. Do you have it clear, or you think it's difficult, or the question? No, based on what we. Let's wait a bit and show now the correct answer. So now after this, we are going to move to the exercise. Yeah. 73. Okay, 73. We are here 3, 10, 12, 17, and online 56. So it's 73. And how many students have replied? 73. Okay, so all of you have already replied. What do you think is the correct answer? B, exactly. Oil flow for hydraulic circuit, okay? Still, I'm not able to achieve 100%. I think I have even given you the answer, but still we don't have the 100%, but okay. Please, what I mentioned, this oil flow for the hydraulic circuit is constrained, restricted, and with that mechanism, we pressurize the fluid, okay? But what the pump is a sum to produce is the oil flow, okay? Is the oil flow. Perfect. So let's move. Are we ready for the exercise for the students online? Were you able to solve the quiz? Yes? Let's move, no? To the exam exercise to review. Okay, so this is the exercise. Basically, we are asked, and with this, I would like you to participate so that I see that if you have understood everything. Okay, the idea is to form the differential and algebraic equations needed to model the output force of the hydraulic cylinder. Okay, so we want to obtain the force of the hydraulic cylinder. Here is the hydraulic cylinder. Okay, and it says the feed and tank pressure are assumed to be constant, and the different components are connected by hose lines. In addition, the assumption that no air has dissolved into the hydraulic circuit is made. So we need to provide the expression of the hydraulic cylinder. Based on what we have learned so far, in the expression of the hydraulic cylinder, what do we need? Which are the elements in that hydraulic cylinder force expression? What do we need to compute? Somebody remembers the expression for the force in the hydraulic cylinder? It was very easy, no? It was, if you remember, perfect. That was the main element. Thank you, Johnny. Pressure times area. So basically, we need to compute the area here that is provided, A1, times the pressure in the piston side. Next, that force is balanced, okay, by the piston rod pressure, no? Which is given by A2 times P2, okay? We are going to denote this pressure as, we will see now how do we numerate, because I will ask you now a different question, but basically this area times the pressure in the piston rod side, and as extra, you can include the friction force, okay? We can have some comment related to the friction force, but basically these are the main components that we need. Okay, so basically A1 and A2 are parameters, okay? Constant in our problem. But pressures, I'm going to call this pressure P2, okay? And this other pressure P3. You will understand now why. Are these pressure constant or are variables in your problem? Are constant or are variables in your exercise, these pressures? They are variables, okay? Because remember, in this hydraulic modeling, what is the equation that models or that give you the evolution of the pressure? Do you remember which was the equation? If you remember, the evolution of the pressure in your control volume can be found in the beginning of week 10 slide, and is given by this, okay? A pressure can be computed using this first order differential equation, and it comes from the lumped fluid theory, okay? This is the time evolution of the pressure, the differential equation, okay? So if you have in the hydraulic cylinder force the product of the areas times the pressures, these pressures are computed from this differential equation, okay? Are computed from here. Perfect. So what we need to do is to apply this differential equation to each of the control volumes of the hydraulic circuit. Remember, and please, maybe some of you have this idea. This equation is not unique for your hydraulic circuit, okay? You have as many equations of this type as control volumes you have in your hydraulic circuit, okay? Is that understood? In your hydraulic circuit, you do not only have one pressure or one differential equation of this type. You have as many as control volumes, okay? So the next question is, how many control volumes do we have in our circuit? Let's go. Let's go, and I want you to reply to that answer, okay? How many control volumes or which control volumes should I consider here? Which control volumes should I consider? Could somebody reply? I will give you now some tricks for the exam to identify these control volumes, okay? But somebody is able to reply based on the tutorials, what we have already done. Would somebody would like to reply?
I think there's three.
Three, exactly. Very good. There are three. Cylinder, okay. We will see now if the cylinder, where can we find the cylinder? But as mentioned in the classroom, there are three control volumes, okay? Any guess of which three? How did you find the three?
One for the A2 or the
Here, no?
yeah, yes, and the hose that's connected to it.
Perfect. So the first control volume that has been mentioned is the piston rod side together with the connecting hose. Perfect.
Yeah.
Good.
Then there's one from the pump until the, I don't know, I can't remember what it's called, but the valve.
Perfect,
Yeah.
perfect. So the other control volume is basically here, well, I didn't mention, okay, but this is the pump and this is the tank, okay? So as components, I think you are already familiar with them. You would have here a pump that is providing the pressurized volumetric flow rate. This is a directional control valve that, depending on how you move it, you have different configuration. In this particular case, you can see that the port of the pump is connecting with this port of this hose, no? So basically the volumetric flow rate is moving through this arrow, okay? So as mentioned, is correct the answer. This is another control volume and is basically consisting of this volume here, the volume of this hose, okay? And why I stop here? Because I have here a discontinuity in the flow that is given by this valve. Remember that this is the symbol of a throttle valve, okay? We have studied three types of valve. One of them was the pressure relief valve that we studied not in much detail, but we studied two valves in detail, learning how to model the volumetric flow rates, which are the directional control valve here, okay? That can provide you different configuration, and this throttle valve, okay? Throttle valve that basically is accelerating the fluid, okay? So as mentioned, of course, the pressure here will not be the same pressure as here. So that is why we are distinguishing from one control volume to other. So this is the other control volume. And of course, the final one is given by this hose and the piston side. Okay? Is it clear, the three control volumes? Any question? So this is the first thing you need to identify. Okay? The control volumes. Now, one question. Well, it's not a question because I'm going to reply it, but each of the control volumes has a differential equation, the differential equation that I showed you before, okay? So we are going to have three pressures corresponding to the three control volumes, and each of these pressures, the evolution will be given by the differential equation. Is clear? And now let's go in detail to compute everything. For the students online, some question about the choice of the control volumes? Clear? We have a comment from Aung about the cylinder. Did you understand that in the cylinder we have two different control volumes? Perfect. One in the piston side and the other one in the piston rod side. Okay? Perfect. Thank you. So everything clear? Yes? Okay. So now, well, this is the reply of the previous question. Okay? Basically, you have here the circuit. You have the pump here. The first control volume is given by a pressure P1, an effective bulk modulus BE1, and a volume V1. What is one question? And we start practicing. This volume V1, how do I compute it? The first thing that you need to ask yourself for these exercises, this volume is constant or is varying? Does it vary?
Constant.
It's constant. It's just given by this hose line connecting the directional control valve with the throttle valve. So it's constant, okay? This second control volume, it has a pressure P2, an effective bulk modulus BE2, and a volume V2. This V2 volume is constant or varying? It's varying, right? Because you have the connecting hose, but you also have this piston here moving that leads to a variation in the volume of this chamber, okay? So of course, V2 will have two addends, okay? The one coming from the connecting hose and this volume in the piston side, okay? And V3, is it constant or does it vary? It's varying, exactly, because again, you have a connecting hose line and this side, okay? Perfect. So V1, V2, V3 clear. About the effective bulk modulus, would you be able to compute them? What do you remember? The bulk modulus provided information about what in the hydraulic circuit? What does it represent? Somebody remember? The flexibility, no? Exactly. It provides an idea of the flexibility inside your control volume. So in this particular case, for the control volume 1, if you want to compute BE1, you have oil here that has a bulk modulus itself, and then you have which component? Just a hose, right? So you have to take into account the flexibility of the hose, okay? But here, for example, in this control volume, you agree with me that I have oil, I have a hose, but apart from that, I have what? A chamber, no? I have a chamber, and the chamber will have a different flexibility. So you basically need to take into account in the computation of the B's all the different components and the associated flexibility, okay? I will show you now in the exercise. Perfect. So the first step, idealization of the hydraulic circuit according to the lamp fluid theory. Basically, the meaning of that is distinguishing all the control volumes and doing this scheme, okay? For each of the control volumes, computing the volume itself, V1, V2, V3, the bulk modulus, and the differential equation for the pressure, okay? The next step is, okay, let's compute the volumes. So basically, as mentioned, for the first one, V1 is just the volume of the hose. That is why you see here H1, because you just have connecting line, hose here, okay? So V1 is equal to VH1. For the second volume, V2 is the volume of the hose, which is VH2. And now I have this chamber, okay? And the volume in this chamber varies because of the motion of the piston, right? So what is the volume of this rectangle here? The rectangular section that would be a cylinder, okay, in 3D in space. How do I compute that volume? You agree with me that is the surface of this piston times this length, no? X1. So basically V2 is the volume of the hose plus this A1 times X1 is this volume, okay? The oil that you have inside here, okay? This volume here. And V3 is just, again, the volume of this hose, VH3, and the volume that you have here, okay? The volume that you have here, which is basically the area in the piston rod side, H2, times X2. This X2 here, don't worry about it. It is not defined, but it's just the difference between H and X1, okay? So it's basically this length here, okay? X2 would be H, the total length in the cylinder, minus X1, okay? Assuming that the thickness of this piston is very small, okay? So basically X2 would be H minus X1. And one question, A1 here, how do you compute it? Imagine that in the exam, you need to provide the equations in a higher level of detail. This A1 is just pi times the radius of this piston, square of that radius. Perfect, it's a circle. And this H2, remember, is a circular crown, okay? It's a circular crown, so please don't put this H2 as A1, okay? This is a circular crown. And if you remember in tutorial 6, in Simscape, we had to write this H2 considering the differences of the two circles, okay, as the circular crown. Do you remember? Perfect. So clear the computation of the volumes? Yes? Perfect. Before that, one question. With respect to the exercise of the tutorial, this cylinder is single acting cylinder or double acting cylinder? Do you remember the difference? Is single acting or double acting? Is double acting cylinder. If you remember in the tutorial, well, the meaning of single or double acting basically was double. Thank you, Ilola. Exactly. Basically, if we have oil in both sides, okay, in the piston side and in the piston rod side, it is double acting cylinder because basically, and you can see even here the hose connecting this control volume and this other control volume, okay? But if you remember in the exercise in the tutorial, it was single acting, okay? We were only providing fluid to this volume here. We didn't have this other volume, okay? Clear? So now let's move to the effective bulk modulus. That is usually the most difficult step in terms of computation, okay? But you will see I'm going to provide you a trick that is very easy, okay? So again, now we need to provide the bulk modulus in each of the control volumes, okay? So remember, for that, you need to take into account the flexibility of all the components. So I'm going to start with the control volume 2, which is more complete or more difficult, okay? Sources of flexibility in this control volume. First one, the oil, no? So basically, remember the equation in a control volume for the bulk modulus was this one, okay? 1 by the effective bulk modulus is equal to 1 by the BO. BO is the effective bulk modulus, sorry, the bulk modulus of the oil, okay? The fluid that you have. Now, you have, and then you have to include the contribution of all the other sources that you have, okay? So in this control volume here, we have the oil, but we have a hose and we have a chamber here, no? Because the oil here is in the cylinder chamber. So we will have three terms, okay? 1 divided by the effective bulk modulus in the chamber 2, in the control volume 2 is equal to 1 divided by BO, okay, the oil, plus, and now let's start with the hose, no? Remember, we need to write the contribution of each of the components. For the hose, we write the volume of the component, in this case, hose, so VH2, okay? The volume of the hose in the control volume 2, divided by the total volume of this control volume, which is V2, and the contribution to the flexibility of the associated component. In this case, we are considering the hose, so we write the bulk modulus of the hose, BH2, okay? Clear? Basically, what you need to know in this structure is you write in the denominator the total volume, V2 here, okay? And in the numerator here, the component that you are considering in the control volume. If we are considering the hose, VH2, and the corresponding bulk modulus in the denominator, BH2 here, okay? So this is V, and this is BH2. Now, the other one, inside the cylinder, well, which volume of oil is covering the cylinder? A1 times X1, no? So basically we have a volume here, which is A1 X1, divided by the total volume, V2, and the bulk modulus of the cylinder is BC, okay? BC. And the term, do you know, maybe you ask yourself, why this term is 1 divided by BO and in the others you take into account the volume? Is this term is as the others, because basically you would have here the volume of oil, but the volume of oil is all the control volume itself, okay, divided by all the control volume itself times BO. So basically you are touching, okay, you are crossing in the numerator and the denominator the all the control volume, okay, clear? That is why in the equation, in the general equation, you always have the term of the oil written like this, okay? Clear, no? This computation. Let's go now, for example, for the first control volume. In this case, do I have oil? Yes. Do I have hose? Yes. Do I have a cylinder chamber? No. So I only have two terms. Very easy, no? The first term, 1 divided by BO. The second term, it would be again volume of the hose divided by total volume times volume of the hose. But in this case, all the volume is volume of the hose. All the volume here, V1, is volume of the hose. So it's just 1 divided by VH, okay? Clear? Perfect, no? And now for the third control volume, could somebody explain me these terms? Based on what we have already learned, it's very easy. And it's always the same, okay? So how do I compute the effective bulk modulus in the control volume 3? Somebody would like to participate? Even the students online, you can unmute yourself if you want and talk, okay? Clear? Okay, at least if you feel lazy, I would like to understand if you have understood it. You have understood it how to compute it, no? Okay, perfect. So basically, again, we have the computation of the oil, okay? The contribution of the oil. Now here, we would have the contribution of, again, the cylinder, okay, in the piston rod side. So this volume here is A2 times X2. Remember that X2 is the total length H minus X1. We have here the total control volume V3 times BC, where BC is the bulk modulus of the cylinder, and now the hose, okay? VH3 divided by B3, BH3. So once you have this, you just isolate the effective bulk modulus, well, you just simplify and you obtain this, okay? Clear, no? Very easy. Okay, so please, this equation, learn it for the exam and practice with this exercise, okay? Perfect. Now, once we have, basically, if you see the differential equation, let me go back to review everything. If we go back to this equation, what we have done so far is computing this VE for each of the control volumes and this V, okay? Now, you need to compute the incoming flow rates, the outcoming flow rates, and the term associated with the varying volume, okay? So now we are going to identify for all of the control volumes, which are the incoming, outcoming flow rates, and the term associated with the change of volume, okay? Clear? So let's go for it. Let's go for it. It was here, almost, we are almost done with the hydraulics. So yes. For example, in the control volume 1, and I ask you now to participate a bit, okay? Let's see if you have understood it. In the control volume 1, if you remember in the previous equation, the incoming volumetric flow rates come with a plus sign, and the outcoming volumetric flow rates in that control volume comes with a minus sign, okay? So in the volumetric flow, in the control volume 1, do I have an incoming flow rate? Do I have an incoming flow rate here? Huh? Yes, which is, okay, which one is it? Without fear, please. It's not, if you make a mistake, it's the first time you're doing this, don't worry. Which one is the volumetric flow rate? QA1, perfect, exactly, is the volumetric flow rate coming from the pump, okay? So you have, basically this control volume has two boundaries, no? The directional control valve and the throttle valve. So the incoming flow rate comes from the directional control valve from the pump and is QA1, perfect. So this QA1, you agree with me that we'll have in the differential equation a plus or a minus sign? A plus. And do I have an outcoming flow rate in this control volume? Yes, which one is it? It's QH2, no? The one coming through the throttle valve towards the control volume 2, okay? So I'm not going to tell you the equation because it's the next quiz, okay? And this is a small spoiler, but it's the next quiz, okay? But you already know how to write it, okay? So, but let's practice before that to the other control volumes, okay? For control volume 2, do I have an incoming flow rate? Incoming flow rate in control volume 2, which one is it? QA2. So a QA2 is exactly perfect, Johnny, exactly. So QA2 is the outcoming flow rate in control volume 1, but it's incoming volume flow rate in control volume 2, okay? It's coming from the throttle valve. So in the equation, I have P2 dot equal to the effective bulk modulus divided by V2, which I have computed them before. Incoming volumetric flow rate, this one is entering. And now, do I have an outcoming flow rate in control volume 2? Is there a line? No, exactly. There is not a line or a pipe that is putting out a volumetric flow rate. So in the previous differential equation that I showed you, you would have QI incoming, the QO, which was outcoming, you don't have, okay? And the final term was, if you remember, this time derivative of the volume, okay? Because of the piston motion. Do I have that term here? Yes, no, because the piston is moving and the control volume 2 has part of it inside the chamber, okay? So I have to take into account that final term, which was the time derivative of the control volume. Let's go back. Control volume 2, V2, was given by this, no? If I write the time derivative of V2, this is a constant, no? So 0. And the time derivative of V2 is a constant, A1, times the time derivative of this variable, no? Which is x1 dot, no? Clear? So that is why you have here minus A1 x1 dot, okay? Coming from the time derivative of the control volume 2. Did you understand that? Yes? Perfect. And I repeat, this minus and this term doesn't come from the outcoming volumetric flow rate. Comes from the time derivative of V2, okay? Because of the piston motion, okay? Clear? Perfect. Now, could somebody provide me the differential equation of control volume 3? Somebody? This one is a bit more difficult, but I want to encourage you to try, okay? So basically, I have already computed the effective bulk modulus in this control volume 3 and the volume 3, okay? Now, do I have incoming flow rates? No, I don't have incoming flow rates. Do I have outcoming flow rates? Yes, which is this QB1 that is going through the directional control valve to the tank, okay? To the tank, perfect. So since it is an outcoming flow rate, which is QB1, you agree with me that I write it with a minus sign, no? Minus QB1. And now, this other term, why does it appear? Somebody can explain? It's because of the piston. In the same way that we had this term here with the time derivative of volume 2, you will have in your differential equation the term minus time derivative of V3. And now, let's see how was V3. V3, if you remember, was VH3 plus H2X2, okay? VH3 is a constant, the time derivative is 0, right? Yes? And now, H2X2. I'm going to write the differential equation instead of using x1, x2, since x2 is related with x1 by this h, the total length. I'm going to consider that I have, instead of x2, h minus x1, okay? Clear? So if I write here h minus x1, you agree with me that the time derivative of that is minus h2 x1 dot, no? You understand that? It comes from here, this relation. We wrote it here. x2 is h minus x1, okay? So x2 dot, you agree with me, that is minus x1 dot, no? So that is the reason why in this differential equation, you have the term minus a1 x1 dot with a minus sign, and in this other differential equation, you have the term associated with the piston motion with a plus sign, okay? But the original equation is the same. It comes from the term minus, could you please explain the P2 again? I will do it right now. I will do it right now. But do you understand the different sign here and here? It comes because of this relation, okay? Because x2 is equal to h minus x1, okay? Clear? Yes? There was a question about P2. I read it correctly. 1 second. Could you please explain the P2 again? What in particular do you need, Tommy, in the explanation of P2? Basically in P2, in the differential equation for P2, for the second pressure, the incoming flow is QA2, so I write it with a plus. I don't have outcoming flow because you can see that we are assuming that we have no leakage and no volumetric flow rate coming out. And this term comes from the time derivative of the control volume, okay? And this control volume is V2, which is A1 times X1. So the time derivative is A1 times X1 dot, okay? Just that. And what you need to know, why do we take control volume into account? We are taking control volume into account because the lumped fluid theory is based on distinguishing on different control volumes and applying the differential equation that we showed to each of these control volumes. I don't know if you referred to other thing, but basically that is why what we are considering the control volume. So did I reply? Let's go step by step. Tommy, did you understand the computation of the P2? Based on the incoming, outcoming flow rates. Okay, if you have any question, just ask me. Amar, did you understand? I mean, informing these equations? Because basically, it's your model strategy. The model strategy that you consider is this lumped fluid theory, and this lumped fluid theory distinguishes in different control volumes, and in each of the control volumes, you apply this differential equation. So basically, you have one equation per control volume, okay? That is why you need to consider each of the control volumes, because you apply the equation for each of them. That is why I have 3 for P1, P2, and P3, okay? Perfect. So now, please, let's go for the next quiz. Yes, of course. Sorry, here or where?
Well, Q1.
Yes.
QA2, are they the same?
I will answer you now because we are going now to write the expressions of the Qs, of all the Qs. So we will go now for that, okay? Thank you. So please go for the next quiz. I think I need to activate it, no? Yes. Basically, in the next quiz, please all go to the next one. We are asked for the pressure in volume V1 can be computed as, and we need to write the differential equation for the first volume, okay? For the first volume. We have already mentioned it. But basically, you need to choose the correct equation. Please, is just in case there is some doubt, okay? Before you reply, stop the finger. 1 second. This is the control volume. Think about the incoming and outcoming flow rates, and if you have any change of volume, okay? And if it's incoming or outcoming, just consider the plus or the minus sign, okay? So which one would it be the correct answer? You have even solved the control volume 2 and 3 that were more difficult, so don't be nervous. It is activated, no? You are able to see it, no? Okay.
Yeah.
Is easy? You have already done it? Yes? Here? Yes? I think so. Okay, let's see how it goes. 62, and here we were 17. I counted before. And online, so 74. 74. So there should be, yes, 69, 5 people left. Let's wait 1 more minute and we continue. Okay, we have 71. Let's wait a bit. And we use this time for resting a bit, 1 minute. Y- Okay, 74. So which was the correct answer? A, no? Very easy. Perfect. QA1 is incoming flow rate and QA2 is outcoming. Okay. So let's show the results. Is A, okay? Only 33%? Oh my God. Okay, I want to clarify this. Did you understand the previous computation of the differential equation? Yes, no? So I hope that, okay, so if students in class replied correctly, maybe the students online, I guess the result options weren't in the same order on our screen. Ah, okay, okay. Okay, so to fix that, I will mention to Aki. Did it happen before? This?
Yeah, but some questions, but now we only had A, B, C, and D, like C on the slides, so we didn't have the options on
Okay,
here, so.
okay,
Would it then be in different order?
okay. Okay, I will mention to Aki this. I don't know to fix this because some of you might lose a bit. I know that quizzes are accounted for in the grade, so I will mention him this, okay? But any case, for me the important thing is you understood the computation of the equation, no? Okay. Okay. So now, okay, so basically these are the 3 differential equations for each of the control volumes. Okay, clear? Perfect. And now, for the previous question about the volumetric flow rate, isn't participation only accounted? It's only accounted the participation, no? Yeah, okay, so don't worry. Okay, so the important thing is that you understood correctly the computation, okay? So perfect. Yes, great. So now, finally, we are going to compute the expressions for the volumetric flow rates, okay? That was the previous question. So as mentioned, we have here, and this is very important, okay? You might have some questions in the exam related to this. So we have these differential equations, but now remember, in the modeling of the hydraulic components, we learned how to compute each of these volumetric flow rates depending on if you were having a directional control valve or a throttle valve, okay? So QA1, you agree with me that QA1 comes from the directional control valve, right? And QA2, throttle valve, and QB1, directional control valve. So based on the expressions that we learned the other day, now we are going to include the expressions in our differential equations, okay? So important, remember, we have a directional control valve, and this directional control valve can work in 3 configurations, okay? When we are going to assume, as is shown here, just in case you have this in the exam, okay? If you have the directional control valve and a plus with an arrow here, it means that you are considering positive, motion to the up here or to the right, okay? If you imagine the hydraulic circuit as we usually do it in horizontal position, the positive motion of the directional control valve goes there, okay? Following this arrow. So for u greater than 0, u greater than 0, basically what is representing this is the directional control valve in this configuration, okay? For u greater than 0, we are connecting the pump with control volume 1, okay? So you agree with me that the QA1 should relate the pressure in the pump with the pressure in the control volume 1, P1, no? And since it is a directional control valve, remember, in the directional control valve, the volumetric flow rate is always this constant CV, which is computed following, for example, do you remember the exercise that we did the other day with the manufacturer curve, and we computed the CV based on the volumetric flow rate and the input signal? We did an exercise the other day for computing the CV, and it is the way to compute the CV in the simulation project work, okay? If you remember that constant. So basically it's this constant times the U. U is the input signal, which is usually a voltage. This sign is the sine function. Remember, this is just a +1 or a -1, okay? This term, the sine function. And this is the square root of the absolute value, okay? And you can see here that we are relating the pressure in the pump, PP, and P1, okay? So this is QA1. And now, for QB1, you can see that in the directional control valve, we are connecting control volume 3 with the tank here, no? So the expression would be, again, the CV times the U. The sine function, which is a +1 or a -1, now relates the pressure in the control volume 3 with the pressure of the tank, and this is square root, okay? Square root of the absolute value of P3 minus PT. This is for U greater than 0, that I repeat, pump connected with the control volume 1 and control volume 3 connected with the tank. If U is equal to 0, which basically is this neutral position connected here, okay? So imagine that now I move down the directional control valve and I'm connecting these 2 arrows with this central position. You can see that there is no connection in the center, so everything is closed, disconnected. So you agree with me that in this case, QA1 and QB1 is equal to 0, okay? That is why for U equal to 0, which is the neutral position, all the volumetric flow rates are equal to 0. And now, if I move this downwards, which means U lower than 0, okay? So basically, my input signal makes the directional control valve moves down. You agree with me that I will connect these arrows with this cross here, no? Cross here, okay? Cross here. So basically, the meaning of that is that now I'm going to connect control volume 1 instead of with the pump, with the tank. That is why you have in QA1, P1 and PT here, okay? That is why you have the connection with P1 and PT. And now I'm going to connect the pump with the control volume 3, okay? So in this mode, with the double acting cylinder, what you are doing is from the pump, you are providing fluid to this chamber here, to the piston rod side, okay? You are providing from the pump oil to this chamber, and you are moving the piston downwards, okay? That is why in this equation, you have in QB1, the pump and control volume 3, okay? So for U greater than 0, remember, the oil comes from the pump to this chamber, and you are moving the piston in up here, you are lifting the piston, okay? And in the other configuration, you are providing oil from the pump to this control volume, and you are putting the piston down. Is it clear how it works? Perfect. So that is why for U lower than 0, you have this equation, okay? Relating the pump with control volume 3, okay? And control volume 1 with the tank, okay? In the other configuration. Is clear? Based on the value of the input signal? Yes? So please, in the exam, I highly recommend you to do this exercise. I will do a similar one if I have time tomorrow, but yeah, it's very important that you practice this, okay? Because of course you are not going to be asked all the parts of the exercise, but maybe a small question for each of the subtasks that we did, you will have, okay? So it's very important that you practice and you write all the equations, including these volumetric flow rates, okay? Yes. Yes. So your question is related to U lower than 0, this one, no?
Yeah.
When the valve, okay. Basically, don't let's say lose yourself in the arrows, because the arrows are made to understand in this particular picture this mode, okay? What you need to understand is that if you have U greater than 0, basically you are connecting the pump with volume 1, and the oil is coming from the pump to 1, and you are putting the oil here, okay? And this oil is coming from 3 to the tank. So basically, this is what I'm doing with the cursor, is what the valve does here. So from the pump to 1 and to the piston, you leave the piston, and the oil here goes to the tank, okay? And for U lower than 0, okay, what you are doing is, from the pump, imagine that you have this square moved here, okay? From the pump, you are moving the oil to the volume 3, you are moving the piston down, and this oil here is coming from 1 to the tank. Understood? You make like an X, okay? Like a kind of a cross or an X, okay? Which is indeed the symbol here, okay? Perfect. Final equation, I didn't mention, okay? I focused on the directional control valve, but of course you have also a volumetric flow rate connecting control volume 1 with 2, okay? Which is because of the throttle valve, okay? Remember that QA2 is this CT that we learned how to compute it, okay? You can either compute it from the manufacturer curves or compute it from different parameters, okay? We wrote the equation the other day. And of course, it is relating the P1 with the P2, okay? This equation, you can see that depending on the value of U, the flow rates of the directional control valve change, but this equation, QA2, is independent, okay, of U. It's always relating the pressure in control volume 1 with pressure in control volume 2, okay? Clear? Yes? Perfect. And finally, if you remember, this is the final step, we were asked about computing the force produced by the cylinder, okay? So the force produced by the cylinder is just the area in the piston side times the pressure in this piston side, which is P2, okay? P2 here, minus the area in the piston rod side, which is A2, times the pressure, sorry, in the piston rod side, which is P3. And now the friction force, you can see here that it has been computed following this model. So if you remember, when we work with the cylinder, I showed you this expression here, okay? For the friction force. So basically, the expression that you can see there is this areas times pressure difference multiplied by the cylinder efficiency, and a function of the velocity. And in this particular case, the function of the velocity that it has been assumed is just the velocity itself, okay? That is why you have this. That is why you have here the areas times the pressure difference minus the areas times the pressure difference times 1 minus the efficiency, and this x dot is just the function that I mentioned before, okay? So here it has been assumed the simplification that the function of the velocity is just the velocity itself, okay? Clear? Perfect. So with this, we have finished all the hydraulics block. We will complete what we need tomorrow in the tutorial. I highly recommend you to attend, okay, to finish all the modeling of tutorial 7. And also I would kindly ask you, I know that I have some questions still to reply by email, but please tomorrow we can use some time of the session for reply some of the simulation project work questions, okay? So please feel free to ask me tomorrow things that you need about that, okay? Any question about the exercise? Clear? Yes? Understood everything? For the students online, everything okay? Everything clear? Perfect. Perfect. We have a couple of reactions. I hope that you were able to follow all the equations and all the exercise. I will, by the way, one thing that I didn't mention, I uploaded, of course, you know that I upload all the tutorial videos to Moodle, and you find the theoretical lectures in the YouTube channel, okay? But I couldn't have access still to the YouTube channel, so I uploaded the previous lecture to Moodle, okay? I will do the same with this lecture, and this Friday you will have all the videos in YouTube, okay? But meanwhile, if you want to practice or study, you can find both the theoretical lecture of last Monday and today's lecture in Moodle, okay? Both of them, but you will have all of them in YouTube too, okay? Perfect. So now I'm going to move to the slides 8, okay? Please, do you all have access to slides 8 right now? I want to comment you just in case that you have some question related to this in the exam, okay? To comment you about this week 8 slides that we didn't do the lecture. So basically, well, since it was after the midterm exam, you have here a summary of the computation of the grade and the objective. The objective of this week 8, please, I understand that you might be a bit tired after the session because it was intense, but this is very important, okay? So please, let's start this. And I'm going to try to explain it to you in the easiest way so that you understand the main idea, okay? And in compensation, because I know that you are tired, I'm going to do a small review for the exam, for the second midterm exam, okay? So please pay attention. If you remember, and now I'm going to go to week 7, we are going to retake the mechanical modeling of the multibody systems, okay? And if you remember, these were the equations of motion of a multibody system, okay, with constraints. So I'm going to ask you some questions. Could somebody tell me this equation, what does it represent? Sorry?
A question,
Somebody,
please.
I think, yes?
Will the second midterm exam cover all the lectures from lecture 1, or it will just be from lecture 8?
Yes. Thank you for the question. I think you will probably have questions from also the content of the midterm exam 1, okay? So that is why I want to do a review, because in any case, you need to know the content of those sessions for the upcoming sessions, okay? But probably, yeah, you can have some questions. But don't worry, because there is not much new content in terms of mechanical modeling, so you will see that it's easy, okay?
Okay, thank you.
Perfect. So, okay, do you remember this equation? What was the meaning of this equation? If you remember, in the modeling of mechanical multibody systems, you had the dynamic equilibrium equations and constraints, okay? Constraints. Why constraints? Because when you learned with Aki that when you model a mechanical multibody system, you use a set of generalized coordinates, and these generalized coordinates are not minimum. So you usually have a number of degrees of freedom but the number of generalized coordinates is usually greater or higher than this the number of degrees of freedom, okay? And these coordinates, these generalized coordinates, are related by these constraints, okay? These constraints. So in the structure of the equations of motion, you have the dynamic equations and the constraints, okay? In the dynamic equations, you have this first term, the mass matrix M times the second time derivative of Q, which represented what? What was the meaning of M times Q dot dot? That term represents the inertia forces, okay? Why inertia? Because you see here the second time derivative of the coordinates, which is acceleration, okay? So this is the inertia term, okay? This other term is the quadratic velocity force vector, okay? And you account for there the centrifugal forces, okay? The centrifugal forces. This QE represent the external forces, and somebody remembers this term that is CQ transpose times lambda. Do you remember the origin of that term? Somebody? Do you know what is that this term? So if you remember, this lambda are the Lagrange multipliers, and this term is the reaction forces, okay? Because the lambdas, the physical meaning of the lambdas is the reaction force with the sign changed, okay? So this term is the reaction forces. So what I'm trying to say here is that in these equations of motion, you have first the dynamic equations and then the constraints that are relating all your coordinates. Is that clear? Yes, perfect. And now if you remember, when you wanted to do a simulation in MATLAB, for example, I will try to do this in the tutorial because I think it's very illustrative. If in someday you are hired by a company, companies usually value a lot programming in Python, MATLAB. So I will try to have a tutorial session with you about how to implement this in MATLAB, so that you learn how to do the dynamic simulation of this system, not only in SimScape, but also in MATLAB, okay? I will show it to you. But basically, if you remember, in MATLAB, you need to jump from this DAE system to an OD system, okay? In MATLAB, you need to do the numerical integration of an OD, and in particular, a first order OD. So in multibody systems, it's very advisable to jump from here to this OD. And to do that, you need to do the second time derivative of these constraints, okay? The second time derivative of these constraints. So that is why you have this structure. So today, I'm going to show you in the last minutes that I have another modeling strategy to write the equations of motion in a different way, okay? And I will show you now what are the advantages of this way, okay? So please remember this structure, okay? Where you have the inertia term, the reaction forces, and this quadratic velocity force vector, and this external force vector, okay? And I'm going to go now to a technique that is called, and you can find it in the week 8 slides, it's called embedded technique, okay? The idea basically is very simple. I'm going to try to explain it to you. You have a multi-body system with a lot of coordinates because you have modeled it in a systematic way, and you have said, okay, for each of the bodies, imagine that I have an arm, the body, the leg. For each of my bodies, you are going to consider the Cartesian coordinates and the orientation angle, no? What happens? The actual number of degrees of freedom is usually lower than the number of coordinates that you are modeling the system with, no? And you have a lot of constraints, revolute joints, given by the revolute joints, prismatic joints, relating these coordinates. So today, the technique that I'm going to show you is how to write the equations of motion with a number of coordinates that is equal to the number of degrees of freedom, okay? So if you remember, for example, in a simple pendulum, or in other mechanical systems, you were considering a number of coordinates that was higher than the actual number of degrees of freedom. What is the number of degrees of freedom of a pendulum? What is the number of degrees of freedom? Do you remember? It's 1, no? 1 degree of freedom. But you remember that we model it, for example, in SimScape, or even I think in theory, you used a higher number of coordinates. So today I'm going to show you how to do it using a minimum number. And the idea, this is the basic math that you need to know, okay, is imagine that you have this Q function which is an expression that depends on y1 and y2. So the generalized coordinates are going to be y1, y2. And you have a constraint that is y1 minus y2 equal to 1. Okay, so the idea is that we are going to rewrite this q in terms of y1, only in terms of y1 using this constraint. Okay, so basically you agree with me that since y1 minus y2 is equal to 1, I can write here this y2 as 1 plus y1, no? I can use basically the constraint inside here, okay? Yes? So it is what is done in this slide, okay? I'm going to write this q or this function in terms of y1, and to this end, I'm going to write y2 as a function of y1. So you can write this function in this way. And imagine that now we want to solve the problem of computing the minimum value. How do you compute the minimum value of a function? You just compute the derivative, no? The derivative. So I'm going to do the derivative of this f with respect to y1. And if you do this computation, you obtain this value. So the value of y1 that leads to the minimum is given by 1 divided by 2, okay? 1 by 2, perfect. And you agree with me that now I can use the constraint and compute the y2, no? Because this minimum value y1 also needs to satisfy the constraint, okay? So y2 would be given by minus 1 by 2, okay? It is what is explained here. So in the same way, the idea here is that you can express this f only as a function of y1 or only as a function of y2 using the constraint, okay? Substituting the constraint y1 minus y2 equal to 1. Is that clear? Basically, instead of using the two generalized coordinates, I want to write this expression as a function of only one generalized coordinate. So that is what we are going to do now in a multibody system. We have the vector of q, a lot of generalized coordinates, and the idea is that now I want to write the equations of motion, reduce the number of equations of motion so that I have as many equations as degrees of freedom. In the case of the pendulum, that I could model only it with the rotation, instead of using a higher number of coordinates, I'm going to write just a single equation because I have 1 degree of freedom, okay? That is the idea of the embedding technique, and it is what we are going to do now. And what you need to know is that to do that, basically, I want to do the following, okay? The embedding technique starts from this equation, which is the virtual work equation that you learned with Aki, okay? With Professor Aki. So basically, you have here the virtual displacement Q, okay? And if you see in this equation, and we compare it with the one that I showed you before, we have the inertia term, no? The inertia term, remember, the mass matrix times the second time derivative, the quadratic velocity force vector, and the external force vector. But we are missing one term. Which one are we missing? Do you remember? We are missing this term with the lambda, the reaction forces, okay, with respect to this one. I can show it here. This term is not appearing. So in the embedding technique, I'm going to try to obtain a system of differential equations so that the number is lower than in the previous case and equal to the number of degrees of freedom, and the reaction forces do not appear, okay? So I will show you now how. What happens? To obtain that, I'm going to write this equation equal to 0. But to write this equation equal to 0, I need that the virtual displacements delta Q are kinematically admissible. Do you remember what is the meaning of that? Kinematically admissible displacements? Basically, the meaning of kinematically admissible displacements is that they fulfill the constraints, okay? So basically what it's saying is that if you have this crank slider mechanism, you cannot move, for example, this piston, let's say here, this solid, this block, as much as you can. You will have a constraint that is depending on this, for example, crank angle, okay? So you need to fulfill the constraints, and those are kinematically admissible displacement, okay? Did you understand that? Yes? Students online? Yes? So basically, I'm going to show you how to obtain these equations of motion starting from that equation, okay? Clear? Yes? Some reaction, last 10 minutes, okay? Last 10 minutes and we rest, okay? Okay, so let's start. What is the idea? As mentioned, I want to reduce the number of equations. So from Q, I'm going to reduce the equations to a number that is Qi, where Qi is called independent coordinates. And this number of independent coordinates is equal to the number of degrees of freedom, okay? So I'm going to split the vector of coordinates in a set of independent coordinates and a set of dependent coordinates, okay? These independent and dependent coordinates are related between them by means of the constraints, okay? The constraints are relating these independent and dependent coordinates, okay? And it is a virtual displacement, so that is why we are using this delta, okay? Because we have delta Q, and we have delta QD and delta QI, okay? So, delta QD is a vector whose dimension is number of constraints times 1. So I have NC, where NC is the number of constraints, dependent coordinates, and I have N minus NC, independent coordinates. N is the total coordinates Q, NC is the constraints. So do you remember this expression N minus NC? What does it represent? The number of degrees of freedom, no? The number of degrees of freedom is the total coordinates minus the number of constraints, okay? That is why I have N minus NC independent coordinates, okay? Clear? Perfect. So as mentioned here, this partitioning between independent and dependent coordinates can be done arbitrarily, but in practical computer applications, usually you use some mathematical technique as, for example, Gaussian elimination, okay? But this is if you wanted to implement it computational. So I think I need to activate the quiz. Anything I need to, we will do the quiz next day, okay? We will do this quiz next day because I want to move to I want to explain at least the idea, okay? So basically, what we are going to do is apply this coordinate partitioning and the total vector Q. We are going to distinguish between independent and dependent coordinates, okay? And now I'm going to show you how to relate the dependent coordinates with the independent ones by means of the constraints. I think there is a comment. Ah, you have already done, we have already done those quizzes. You have already done, but you have already done this lecture? No? Okay. Maybe, okay, maybe the quizzes were launched other day or were activated, but I think that this coordinate partitioning, you have not studied it yet. But thank you, Johnny. Maybe they were launched other day and I am not aware, okay? So, okay. The idea is that now we are going to use the constraints to relate the dependent and independent coordinates. Did you understand so far the big picture? Yes? Okay. So now what I'm going to do is here you have these coordinates that were C equal to 0, no? So if we consider a virtual displacement, okay, and we compute the delta C, okay, a small variation, you agree with me that delta C is just given by this equation, okay? Distinguishing between independent and dependent coordinates, okay? Remember, delta Qi independent coordinates, delta Qd dependent coordinates. And these matrices, CQi, CQd, are just built from the columns of this total matrix C, okay? By the way, this CQ, remember, is the Jacobian matrix of the constraints, okay? The Jacobian matrix. So I need to choose now in this Jacobian matrix the columns associated with the dependent coordinates, and in this CQi, the columns associated with the independent coordinates, okay? And now you agree with me that from this equation, you can isolate the delta QD, the dependent coordinates, as a function of the independent, right? You can express these dependent coordinates as a function of the independent. And it is done by means of this equation, okay? You can read here that the virtual displacement of the dependent generalized coordinates delta QD can be expressed using the constraint equations as a function of the delta QI. Basically, isolate this delta QD as a function of delta QI, and you obtain this equation here, okay? this equation here, okay? So delta QD is equal to this matrix CDI, which is given by this expression, and as a function of delta QI, okay? So you have here this relation between delta QD and delta QI. And now, since we have related delta QD with delta QI, you can write the total virtual displacement vector delta Q as a function of delta QI, okay? As a function of the independent one. So you can see here that in delta Q you have delta QI, delta QD. The delta QI I keep them as they are. And the delta QD, I'm just going to substitute them here, okay? As you see them here. So now I have a relation between delta Q and delta QI, where I is an identity matrix. And now, if you remember this equation that we started with, now, since this delta Q is a kinematically admissible displacement because I use the constraints to relate the dependent with the independent coordinates, I can set that equation equal to 0, okay? Equal to 0. So basically, this equation now can be set equal to 0 here, okay? And in the delta Q, I can use the relation between the total coordinates and just the independent ones. So this equation here is what is called the equations of motion using the embedded technique, okay? Using the embedded technique. Difference with respect to what we have done so far. In the augmented formulation, this is very important, please, this is a summary, okay? In the augmented formulation, you had the equations of motion considering the constraints here, okay? You have the constraints here with this lambda. So that is why you see here the modeling of the crank slider mechanism considering the reaction forces in the revolute joints, okay? In the embedding technique, since we have expressed the delta Q only in terms of the independent ones, that is why, and you don't have the term CQ transpose lambda, the reaction forces, that is why you have this picture here. You don't have the reaction forces in this picture, okay? Because we are not considering the lambdas, okay? And remember, this would be the equation of motion using the embedding technique, and this is the relation between the delta Q, the total number of coordinates, with the independent coordinates, okay? So just to summarize, please, could you reply to this question? The number of independent coordinates is equal to what? Number of degrees of freedom of the system, okay? Number of degrees of freedom of the system. So I'm reducing the number of equations. And now my differential equations, instead of having here the Q dot dot, I want to write them in terms of the QI. So basically the idea is that I'm going to use a projection from the total number of coordinates to the independent coordinates, okay? I'm going to translate from the language of total coordinates to the minimum language, let's say, using the minimum number of coordinates, okay? But that will be the next day. I will talk with Aki about, because we have still some slides. I think that the important conclusion of today, you understand the purpose of this? Did you understand what is the modeling purpose? To reduce the number of equations and provide a formulation without the reaction forces. So that is the main conclusion. We will continue the next day. Thank you so much. And please, tomorrow in the tutorial, attend. I'm going to finish the modeling of the hydraulic components for the simulation project work, okay? And do another exercise. Have a good evening. For the students online, if you have some questions, just let me know. Okay, thank you, Johnny. Any question, just let me know. Bye. Have a good evening. I'm going to stop recording.